welcome back. This afternoon we have a couple more talks. Is this working? Okay. Welcome back from lunch. This afternoon we have a couple more talks. The first talk will be by Bin Yu, who's at the University of California, Berkeley, and she's going to talk about some work that both uses Lasso to both estimate covariates as well as the effect size.
Well, I'd like to thank the committee for inviting me. Has been really enjoying myself. So this is joint work with people from Berkeley, graduate student Adam and postdoc Hanzhong, and my colleague who just spoke, Jess, and also with a colleague from Rutgers, Chunhui Zhang. So I started interested in this problem while I was doing some consulting on A/B testing with an IT company in South Bay, in the Bay Area. And the question was, I was actually advising them to do post-stratification based on some earlier work we did with Luke and Jess. And they come back saying that we have more and more covariates, should we just keep adding on? I managed to convince them that don't do that. And then I started thinking about the problem. So you should use some of the large data, available big data, but at the same time, definitely don't want to use all of them. So that's the beginning of this project. And for illustration, we don't have access to the data. We tried to get the data, actually, was too complicated with lawyer and everything, so we're going to use some other data to illustrate. And in terms of the big data connection, it's very much building on the computation power, which has been developed for Lasso, and also theory, which has been going on for the last 15 years. And I'll comment on the complexity while we go along. So I'm not particularly running on big data, but the implications there. So here's a roadmap. I will start with data randomized trial in medical practice on some invasive device to monitor critical ill patients, and then do my notation on name and Ruby model, and formally introduce Lasso-adjusted treatment effect estimator, some theory, and then finish with the data and simulation from the data. So this is from Wikipedia. It's some device called PAC, pulmonary artery catheter. So it's something you put from one of the veins, or the doctor put from a lot of time from the back into the heart to monitor the status of the heart. And it's invasive and expensive too. The question is, does it affect patient survival, say 20 days mortality rate? We'll be looking at something a little different, adjusted life quality measure. There was a study in 1996, it was an observational study done in the US, 15 university hospitals, about 5,000 patients matched with control. It's a prospective cohort study, and they find non-trivial adverse effect on patient survival and also on increased cost of care. So it seemed to be, and then they said that we need to have a randomized trial to study this. And the randomized trial came 2005. Was done in the UK, and was a selection of university hospitals and otherwise intensive care. About 65 of them, was about 1/5 of the intensity care units in the UK. And after some data processing, there were 500 patients in the treatment group and control. And just to make a comment that the previous study, I believe the control really are the people who didn't have PAC. But for the control here, it's a little complex in the sense that the control protocol was that the hospital could choose not to have PAC or have other monitoring device. So you can see that not exactly matching the observational study, but nevertheless, it's very related. And the outcome variable we'll consider in this talk is quality adjusted life years. And many of them, you see that 60% are pretty small numbers. People didn't survive very long. And there are 59 covariates, age, and a lot of physiology and also kind of health status measures, and about the intensity unit size, about the hospital, so 59 of them. If you want to look at interactions, you look at the second order, quadratic and first order interactions, you quickly go up to 1,000. Okay, so you quickly have P close to the size of N. And if you go to higher order, your P will exceed end very quickly. So for the IT company consulting, the N will be millions, and P could start with a few thousand, but if you look at interactions, quickly you go to the millions too. So it just goes up really quickly, and the question is, should you take advantage of the availability of big data and do some selection, do better, or how far can you go? And if you can select fewer variables, it's also cost saving in terms of future work, collection, and also data storage, communication. So there are a lot of advantages for feature selection on top of do better job in terms of adjusting for estimating treatment effect. So let me give you the punchline first. I think Judeo did that, so I happen to have the same strategy. Is that you look at, so what we did is we did a genetic matching to get some kind of real fake data in the sense that some of the outcomes are observed, others we just did matching and made it up, and then we have a finite sample, and then we did a randomization to this finite sample. We now both know the two outcomes in practice, usually not possible, and we shrinked the sample size to match the size of the covariates, which is 59, and then we did some random many runs. So you can see that this is unadjusted. This is from 500 runs. And if you use all of them, OLIS, you have a huge increase. You took, basically, it's overfitting. And then if you do Lasso selection, two versions of it, you do better. That's basically the punchline of the talk. You do better, and and on top of that, you also, for this one, you end up with like 5 covariates to look at, which is quite telling. It's not causal, but it's definitely good predictors, and they seem to make sense. So for me, it was also interesting to study Lasso, which my group and many other groups did a lot of study under the linear sparse models. So you assume there's a sparse linear model, and then you look at how Lasso works. And this Neyman-Rubin model, very much because we're reading Winston's paper and also Friedman's paper, gave me a way to look at things like misspecified model and look at Lasso. I think was quite interesting. And of course, theory cannot study everything, so we also argumented with simulation and real data studies, and then look at variants of Lasso, because Lasso have by now many, many variants, and one particular one we found quite useful here. So this was introduced already, I think, in Thomas' talk, is one of the key assumptions for us to be able to describe and discuss the Neyman-Rubin model, which is something called stable unit treatment value assumption. The first assumption is no interference. It means that the PEG patients, their outcome, their adjusted quality of life, won't be affected depending on what other patients have or have not, which seems to be quite sensible here. The second one means only a single version of each treatment level. That means there's only one PEG, which is not as plausible, because one thing is there's a duration of time the catheter is left within the patient's body, and that varies. So it's not just, and also the time one is put in, and that's left, I think, to the discretion of the practicing physician. So this is for the data. It's not exactly kosher, but we're going to start doing the inference, not addressing this issue. And with this assumption, now I'm allowed to talk about two numbers, the two potential outcomes for patient I under treatment and under control. The different versions, if they are not, there are multiple versions, technically I should have a version index there, because the outcome could be different. So now I'm already assuming that the versions don't matter, and there's only one outcome associated with one patient, one treatment, or control. And then the parameter of interest is the average treatment effect, ATE, which is the average difference of the potential outcome in this case is life quality, quality of life adjusted life years. And they're all fixed numbers here. There's no randomness so far, okay? And what happens is when you do randomization, which I'm assuming sampling without replacement, again, there's a little description from how the trial was done because they didn't have fixed number of patients and did something without replacement. They basically did when patient comes and they had to call some telephone service, whatever, and get a random assignment. So there's also discrepancy from the theoretical analysis from actually how it was done for that trial. So the difference here, all the A's and B's are fixed. What's random is the random assignment. The indicator whether each patient is assigned to treatment equal to 1 or control. And I end up with 2 random sets. The people end up in the treatment group and the complement of that, which is the random set of control group. So everything here in terms of mathematics end up dealing with random sets, a summation over a random set. That has some interesting characteristics mathematically. And then the observed is if you are in the treatment group, your potential outcome become your outcome, which is AI. If you are in the control group, your potential outcome in the treatment become your actual outcome, is BI. So this is a good, concise way of indicating the the observed outcome in terms of potential outcome and the randomization mechanism. So TIs are random, the little A's and B's are fixed. And the A's and B's are results of the randomization, so they are random. And we look at the ratio of the non-people in the treatment and the non-people in the control. They are more or less 50% for this case. And you have this quantity, which is not observable because half of them, or close to half of them, don't have this outcome and the treatment because they're in the control group. And this is what they observe. It's the average of outcome for the people end up in the control group, treatment group. This is end up in the control. Again, I emphasize A and B. They are random, okay? And the little numbers, AI and BI, they're fixed. So you have fixed list of numbers, you random pick them and do the averaging. And the simplest estimator is the unadjusted, which is simply take the average outcome from the treatment group minus the average outcome from the control group. We have the unadjusted. But as in the IT company project A/B testing, and also here, you have many, many covariates could be highly correlated with the outcome. But in this case, as we discovered, to age, right? If you're older, your survival rate is just lower, no matter what. Then can we take advantage of that to get better estimates of the treatment effect than using the unadjusted? So you have people in the treatment and people you didn't pick in the control. Can you use that to help getting better estimates? And next slide, I'll tell you the other, but the work directly related work, which we really have a very close relationship, is this new recent paper by Winston, who was following up on some early work by Friedman, but what he did was very creative, was to add an interaction term of the treatment versus the covariates, and this way he can show that if you do adjustment this way, you will always do better than unadjusted. Under Friedman's case, you have conditions, sometimes you do better, sometimes you don't. But with this added covariates, which is interaction, then you basically end up with 2 sets of adjustments. So you have a set of adjustments, coefficients for the treatment group, and a set of coefficient adjustment for the control group. It's easily seen that the square minimization is equivalent to 2 minimizations, 1 for the treatment group and 1 for the control group. Because if you take TI being 0, you end up with the ones with here, and they're different. So it's easily seen that you end up with two least squares. Instead of having one, have the shared adjustments. So basically, this allows different adjustments for control and treatment. And then you have adjusted OIS, adjusted ATE, which is the average from the group with adjusted average and adjustment for both groups, and you take a difference. You can also look at this as you imputing the other potential outcomes using the covariates which you didn't observe. It's kind of equivalent. And you end up with, hopefully, better variance, which is indeed the case asymptotically, under conditions which we will inherit for our Lasso analysis, which I'll tell you next, is that you asymptotically do better than adjusted. But what if p is larger than n? So for the PEC case, if I get the quadratic and also second order interactions, I easily end up p equal to 1,000 and have my sample size like 1,000. It's very comparable, and that's what I did. And you can just also add other polynomial and splines. And in the IT case, you just have many, many, many covariates to start with without even doing the interactions. So definitely we're in the world of p larger than n. And Lasso has come now for the last 20 years, become a modern version or modern of model selection. If you go back to the 70s, right, we had AIC and BIC for model selection, and when p is large, those combinatorial problems become impossible to do, but even we actually in practice do forward and backward selection, so we never really went for the combinatorics. But Lasso, which is closely related to L2 boosting, which is like one way of doing forward and backward. And there were, of course, earlier papers than this one, but this is a typical reference. The algorithm, actually, the homotopy algorithm for solving Lasso can at least trace back to a Markowitz paper in 1950s. So, but this is really giving the name of Lasso. So instead of, remember in Winston's paper, we had OIS adjustment, this part, these squares. And since p is very large, quickly you either have to go for generalized inverse, which we know usually overfitting, then you do penalty. So kind of implicit assumption is that there's some major covariates that are outstanding, and hopefully we can go for those. But even when you don't have that, you have to say that I cannot go for p, which is the same order, and I need to shrink down anyway. So you might want to do selection even this doesn't hold. The theory, which will show, kind of assume a weak sparsity assumption for the theory to go through as it is for now. So if you look at it, you have two regularization parameters which control separately how much sparse you want to impose on the adjustment for the treatment and how much you want to control for the adjustment for the control group. So you have two parameters. And again, they separate into two Lasso problems, same way as in the least square case. And if you relate back to the Lasso literature, which has seen lots and lots of theoretical work, and many people in the audience probably have done work there, we kind of, here is really you care about the predictive value. You're not really interested in individual betas, but you're interested in this predictive value in some as adjustment. And this again separate into two separate Lasso problems, one for the treatment group, one for the control group. So the difference between the typical sparse linear model analysis is that instead of you have random summands in the linear model case, you have, all those are fixed quantities except the summations is over a random set, which is the randomization set. Okay? So that calls for some need, some concentration inequality for random sums. And I should comment that there has been much development also in terms of fast algorithms. The one we use is in R by Friedman, GlimNet. And in the worst case, when the path following algorithm, which is not very the best for p much larger than n, is kind of exponential, not polynomial. But when you do some gradient descent type approach to solving this problem, become like NP, but often you stop early, it's like more NS as the sparsity. So it's kind of linear, a little bit multiple of linear if you have actually major predictors or covariates you want to choose. And then you can similarly define the Lasso adjusted ATE estimator, very similarly the same way as you would do with OIS, except now you have the Lasso estimator. There's a hidden regularization parameter there. There's a hidden regularization parameter there. In practice, we do cross-validation, and in theory, we kind of fix a certain rate. There's a gap, also in the usual Lasso literature. So what we're interested in is really, I'm hoping this misspecified model in some of the name a Ruby model. It's not exactly the model you assume generate the data, but you're using this Lasso method. It allows us to see something which will be relevant in practice, especially about transformation. If you assume the sparse linear model, the transformation problem, which is very, very relevant in practice, gets assumed away because you already have the right form. But in this model, you can discuss. You have all these covariates. Should you do some transformation before you do adjustment? And this framework can accommodate that. And we also want to recover the same thing as in Winston's paper, like do we have asymptotic normality, under what conditions, and can we estimate? Actually, we have a conservative estimate asymptotic variance. And now it's already mentioned in speaking that there was this Winston's paper and the two earlier papers by Friedman for fixed PKs using OIS under the name of Ruby model. And recently they have a flurry of papers kind of looking at treatment effect adjustment, but still assume versions of regression model. Might not be linear, but there's some sparsity hidden there, maybe nonlinear, so that's the other line of work, just very recent. We haven't gotten to the bottom of all the technical proofs yet, but not under the name of Ruby model. So now I want to make some assumptions to set up the stage to give you the statement of the theorem. So this is just an index set for the treatment covariates, and we have to assume that there's some projection that in a linear form that it's a good approximation in some sense to the potential outcome. Okay, so we assume there's this beta you can project. This is just a difference. And this is fixed. This is all fixed, we're assuming, but we do assume that these two kind of weakly dependent. Otherwise, you have a problem. In the OIS case, they happen to be, if you do OIS projection, they are orthogonal, so you don't have a problem. And you put them all the relevant covariates together, you have a set. And all these quantities are fixed. And this set of conditions, which are quite telling, it's already in the Lin work, saying that it's all required for central limit theorem. If you look at the most important theorem for statistical inference, probably central limit theorem or concentration is something say that things will stabilize. We're not going to see very transient behavior. All these conditions basically are needed for that. They might not be the weakest possible, but some moment conditions are needed for central limit theorem to kick in for things to concentrate. So this is about that, and this is pretty atypical. So it's both on the covariates and also on the error terms. And some moment convergence, second moment convergence for the error terms. And for the high dimensional case, I need more notation. So I need to now indicate, use denote S, the sparsity, which is the number of non-zero coefficient in my approximation, and I need to control the dependence or projection between the error term and my kind of sparse approximation. And this can grow a little bit, but not too fast. The condition we need is that this projection or this weak dependence should be going to zero faster than S square root of log n. So when it's n large, it's small, so you have more and more stringent condition on how much you can allow. And you need some kind of convexity condition. If you look at Fisher information, that's basically, you want Fisher information to be positive, for things to be well estimated. It's really Hessian. It's a convexity assumption. In the low dimensional case, it's basically about the eigenvalues. In high dimensional case, for the ambient space, you couldn't possibly have the Hessian low bounded because you have not full rank. However, what we learned in the linear model sparse literature is that you only need convexity in a cone, which is kind of low dimension, and that's what's saving you. So you don't need the convexity in the ambient space. You need on the low dimension space, under sparse models, under things that sparse, you need convexity on that cone, kind of low dimension, and you're fine. So that's kind of what we're asking for. It's a little weaker than the restricted eigenvalue condition, but it's nevertheless related, very much similar. And then the same way as in the sparse linear model case, you need the regularization parameters have to decay relatively at this rate. In practice, we use cross-validation. Okay, nobody has been able to analyze cross-validation theoretically. So there's a gap. And then not just, this is typical in the linear model analysis. Here we have to add the dependence. If you have a very, but we control that already here. Okay, so the error term in the approximation with the covariance cannot be too dependent. It's kind of the weak additive sparse model, I would say, assumption under the Neyman-Rubin model. Then you have a pretty familiar result, saying that then the Lasso adjusted ATE has asymptotic normality, and with a variance quite similar in the OIS case, and then you can show that it's always better than the unadjusted case. But this you have to estimate or bound because you cannot get it, and then you have a conservative estimate. So one thing for me was very interesting to see like whether the theory tells us anything useful in practice, which is I concern myself with that. I think the moment conditions, which already in Winston's work, are quite telling. Is that we did simulation to wireless condition false moment. We did T distribution has very high false moment, all that the asymptotic normality in the simulation fall apart. Okay, so you need some for concentration to happen, and also you need some convexity condition that you can also show that when you push that, the asymptotic normality also fall apart. However, even in those cases, seem the mean square error still better, right? You might not be able to get confidence intervals, but there might be other way. I'm not sure when you lose asymptotic normality whether bootstrap will still work, but you do have mean square error still seems to be smaller than unadjusted. And a new result, actually Chen Hui came out with, is some useful, I think, concentration inequality dealing with the Neyman-Rubin model, which I think other people might find useful, is that the previous concentration inequalities with sampling without replacement usually need bounds on the potential outcomes, if you come to that case, but we were able to remove that and to get exponential sub-Gaussian bound on a random sum. Remember, I kept emphasizing I have random sum instead of sum of random variables, as in the linear model case. So this could be of interest, independent interest. And the proof was quite interesting. It's going back to the Hofting paper early on, and then he had a kind of a general result. And then with some self-thresholding or envelope development, you can get this bound. Really, Chen Hui did it. And for the variance estimate, you can go to similar thing as Neyman did. You bound this term and by these two terms, and then you have a conservative estimate. And for each individual ones, for the error in the treatment group and control group, we do the degree adjustment. And that's important because we have sparse models. We just count how many non-zero coefficients we fit. And then we have the degree adjustment variance estimate. And that's conservative. You can show that. Okay, so now back to the Pacman data, the randomized trial. This is the 95% confidence interval used unadjusted with a conservative, I think, variance estimate. This is the OIS, and this is Lasso. What I mean by CV Lasso is that you use cross-validation selected parameters, and then use Lasso estimate in the adjustment. What's CV Lasso plus OIS? It's a variant in an earlier paper Hanzhong and myself, is that you carry the whole thing through. For fixed lambda, you do Lasso, you do the OIS bias correction, and then you select. So you select on this two-step estimator, and it gives quite similar result, but I will show you later, this procedure ends up choosing much, much fewer covariates. And I think we seem to want to recommend this one. Okay, and in terms of computation, it's a little heavier because every step you have to do OIS. And, but you can have a warm start. I don't think it will be that costly if you have a fast Lasso algorithm already. So these are the size of the intervals. You can see that even nothing significant, but definitely there's going this way, and we're using a conservative variance estimate. If we don't, possibly we're kind of on the borderline. So that's what you saw already, that the Lasso and the Lasso plus OIS CV was subject to over 1,000 covariates, and OIS is only 59, and we got shorter intervals. In general, all the regression-based method, the Lasso and adjustment got a little shorter, but not too much. The key is that from 59, Lasso select 28 and 8 treatment and control, and these ones select very, very few. Okay, and if you look at them, they're very, very sensible ones. Age square, and age interaction with some like a state of health, state of heart selection variable. So it's quite a big reduction. That's in terms of the benefits, that's one thing. And that's, so what we did then, we did this, we imputed the unobserved potential outcome and end up having now a data set with both outcomes, and then we did randomization. So this is a simulation study based on the PAC data. If you take a look, the bias, pretty small to the third digit, and the standard deviation, you can see reduced for all the 3 adjustment methods, and the coverage, they're all over coverage because it's a conservative variance estimate, and the length quite comparable for the adjustment. But here's where you see a difference. So of course, OIS by definition use 059, and Lasso cross-validation selected 25 over 1,000 variables. So that's a huge reduction. And for the control, selected 15, and Lasso plus OIS reduced much, much further to 6 and 4. This is the average over many, many runs. Okay, so this is a huge reduction, and it's something definitely you can look at. And we look at them, they are very sensible. Age, definitely, and age interaction with some heart status variable. Another thing is, all these variables, if you want to interpret or want to look at as an indicator for subgroups, are they stable? So again, in the simulation study, because we have this data, we simulate by doing different randomizations, and you can see that the triangle is the method we like. It's still a little unstable, but much more stable than cross-validation and Lasso. These are the frequency probability. So what I did is, we had the first 59 original variables, and then another 10 because the square term, most of the variables actually indicators, square term is the same. And then you have the first order interaction terms layout. So that's why we have over 1,000. And this is for the control group. So this is all have something to do with age. You can see that this is not just giving smaller number of covariates selected, but also more stable. So hopefully, I think that's an indication that you might likely to get more interpretable variables than cross-validation Lasso. They are just 2 variants of each other. And with much fewer variables, if I look at the x minus x bar times the coefficient, that's called the adjustment value for the Lasso and Lasso plus OIS, they more or less agree. Okay, so this is saying that even I use only 5 covariates, this is used like 25 or more or less, then they give very similar adjustment values. So not much is lost in terms of adjustment. And because you take a difference, so the final adjusted ATE estimate, actually they more or less the same. They both a little bit more. So the adjustment value from this method is a little higher for the higher values than the one based on Lasso only. But since you take a difference, so the end result are not that different. Okay. And so here's a summary. So we carried out a statistical analysis under name and Ruby model. It's also a misspecified model for Lasso, so it's kind of interesting, and confirmed all these moment conditions already in earlier work. They're important. And we're thinking about following up to do transformations and control the false moment and make sure the second moment is not too small as a way to do transformation. But that hasn't been done yet. And we have a new concentration inequality, I think possibly useful for other people doing analysis under name and Ruby models. And I think we are quite comfortable recommending cross-validating Lasso and OS. So in the earlier paper with Hanzhong, we also had good performance there. So it's not just based on this work, but there were small simulation studies. The highlight is for this method is actually much fewer variables and more stable, and with similar coverage and confidence intervals. Thank you.
So I'm actually surprised to see that you actually select quite a different set of covariants for the treatment group and the control group, right? Because one of them is like 24, the other one is 8 or something. Like, what is the intuition behind it? Can you offer some of that?
Well, I think a lot of them could be the thing is, a lot of them could be very highly correlated, so I don't know what in real, they're that different. We have to investigate that. For the other method, actually quite consistent. There's only one difference. There's some correlation among the covariates. So when you have that, what's being selected are not always stable, as you saw from the stability plots. So there could also be a different mechanism for what's driving the outcome for two groups.
Okay, so why is it that you're actually fitting using a different selection for both for treatment and control? Why not doing a combined?
As combined, and as even earlier work without the Lasso step, you can show that it's not always better than the unadjusted.
Okay.
Yeah. So we inherited that insight. Yeah.
Okay. Thank you.
Okay. They overlap. I think the one selected by the smaller group is a subgroup, and the other one is bigger. I think a lot probably because of the correlation. Yeah.